Welcome to the video solutions of CodeDrift. Hi everyone, so today in this video I will be discussing the problem swap it. Okay, so the problem says that given an array of integers a with values 0 to 9, find if the number of allowed neighboring swaps b are enough to arrange the array into another array x which produces such array z which has the greatest prefix sum at each index. That is to say, no other arrangement of array Z exists that has for any index I a greater prefix sum value than that of the obtained Z array at the ith index. Okay, the Z array is produced using the following rule from the array X, that is Z of I is equal to sum of the first I elements in X minus sum of the last I values in X. Okay, if the number of allowed neighboring swaps b is enough, then return 1, otherwise return 0. Okay, so the problem says that you will be given an array of integers a where each value in this integer a will be from integer array a will be from 0 to 9. What we have to do, you can just rearrange or reorder the elements in the array a to obtain another array x. Okay, so let's say you rearranged some of the elements in array a and got another array x. Now from this array x you will produce another array z where the ith element in the array z will be equal to sum of the first I elements minus the sum of the last I elements. Okay, so in this way you will produce your x, you will produce your z. Fine. Now what you need to do, you need to calculate the prefix sum of this array z. So let's call it p. So what your objective is to maximize the value of p of I for all the i's. So what it means is that after you got your prefix sum array from z, let's call it p1 p2 up to pn. So the objective is that p1 should be as much high as possible, p2 should be as much high as possible. So for any index I, pi should be greatest of all the possible p's. Okay, so of all the arrangements that you can do to x which can produce z and from where you can get p, this array p should be having, like, all the elements of this array p should be having as high value as possible. So let us consider an example. So let's say your array looks like 132. Okay, it consists of 3 elements. So what we can do, like, let us say that we don't change the order of this array. So if you don't change the order, your z array will look like this much. Okay, so it is like the sum of the first one element minus sum of the last one element. Okay, so 1 minus 2 is minus 1. Okay, then you calculate the sum of the first two elements, which is 4. So 4 minus the sum of the last two elements, which is 5. So 4 minus 5 is again minus 1. So you will write minus 1. Then sum of all the first three elements minus the sum of last three elements. So that would be the sum of the entire element. Okay, so the sum of all entire element of the array minus sum of entire element of the array would be 0. Okay, so this is the way your z array look like. Now what you will do, you will find the prefix sum on this array. So that will be minus 1, then minus 2, and then again minus 2. Okay, so this is the prefix array that you will get if you don't change the order of the initial array. But let us say we change the initial order of the array so that it is looking like this now. Okay, so let us say this is the way it is looking now. So what you will do, you will now again find the z array of this. So so its z array will look like, so 3 minus 1 is 2, then 3 plus 2 5, 5 minus 3, so that will be 2, and then again you will get 0. Okay, so basically you find the sum of first one element minus sum of last one element, you will get 2. Sum of first two element minus sum of last two element, you will get 2 again, and sum of three elements, first three elements minus sum of last three element, you will get 0. So this is the your z array. Now you will find the prefix sum on this array, so it will look like 2, 4 and 4. Okay, and by the way, prefix sum is basically calculating the sum of the range 1 to I. So you start from the very beginning of the array and calculate the sum of all the elements up to a particular index I. So that will be the value of the prefix array at the ith position. Okay, so that is called a prefix array. Now what we will do, as you can see, that if you compare this array and this array, you will find that all the elements of this array are basically bigger than the corresponding elements of this array. Since it is 2, 2 is bigger than minus 1, 4 is also bigger than minus 2, this 4 is also bigger than minus 2. So you see that all of these elements are basically bigger than all of the corresponding elements of this array. So you can try out various orderings of the initial array A and you will ultimately find that you cannot get anything better than this. So it means that this is the final prefix sum, which is the best prefix sum array, since all of these elements are reached to its maximum value. Okay, and how we have reached this? We have reached this by rearranging this array to this array. Okay, and you will find that except this arrangement of the elements, there is not any other arrangement of the array A which can produce this prefix sum. So essentially what it means is that you are given the initial array 132 and you have to rearrange it to 321. Okay, so let us see what can be the minimum number of adjacent swaps which are required to convert this array to this. So how you can do this, let us see. So as first of all, you can see if you swap this 3 with this one, you will get 3, 1 and 2, and then if you swap this one with this 2, you will get this thing. So it means that minimum number of adjacent swaps needed to transform this array to this array is 2. So it means that if b is greater than 2, if b is greater than or equal to 2, so it means you are allowed to perform more, or you can say at least 2 adjacent swaps. So in this case your answer would be 1, which means it is possible. Otherwise, if b is lesser than 2, in that case your answer would be 0. So let us now discuss an optimal approach. So in an optimal approach, what we will do, we will try to convert the array into a descendingly sorted array. So a descendingly sorted array means that the every next element is basically lesser than or equal to its previous element. Okay, for example, this is a decreasingly sorted array, or you can also say that this array is sorted in reverse order. So after converting this our given array into this array, we will try to find out what can be the minimum number of adjacent swaps needed to convert our given array into a decreasingly sorted array. Okay, so we calculate the minimum number of steps needed to convert the initial array into a decreasingly sorted array. After that, once we have found this, we can simply compare it with b. Like if b is greater than or equal to this number of swaps, then we can say that the answer will be 1, otherwise it will be 0. So let us try to get the intuition behind like why we need to convert the array into a decreasingly sorted array, or like how converting the array into a decreasingly sorted array guarantees that the z array which will be produced by it will give the maximum prefix sum array. Okay, so let us try to say or try to see why to convert the given array into a decreasingly sorted array. So let us consider this with an example. So let's say you are given this array which is 5 1 3 4 2. Now you know that okay, I have to convert this array such that after that I will be calculating the z array out of it, right? You will find the z array out of it, and after that you will find the prefix sum array out of it, right? Now you want to get the maximum for the first element. Okay, like you want it for all the elements, but let us try to focus our attention on the first element of our prefix sum array. So let us try to think what can be the maximum value of the first element of our prefix sum array. Okay, so you know that the prefix sum array, or the value of the element at the first index of the prefix sum array will be same as the first element of our z array. Okay, so maximizing this thing is same as maximizing this thing. So what, let us try to think what can be the maximum value of the first element of the z array. So that would be nothing but what can be the maximum value of the first element of the z array. So you know that the first element will be obtained by subtracting the minimum, or like subtracting the sum of the, like subtracting the last element from the first element of the transformed array. So if we transform this array in such a way that the first element is equal to the maximum one and the last one is equal to the minimum one, then you know that this maximum minus minimum will give you the maximum difference. So this first element of the z array will be maximized by it. Okay, so what we will do, we will try to see okay, what is the maximum of this array, that is 5. Okay, so it means that in an optimal array you will place 5 at the very beginning, and you will place what is the minimum in this array, that is 1. So you will place 1 at the end. Okay, and if you place it like this, you know the first element of your z array will be 5 minus 1 4. Okay, now once you placed 5 and 1, you are left with 3 4 and 2. Okay, now again if you apply the same logic, so your prefix array at the first point will become 4. Now you will try to maximize the second element. Okay, so you have fixed the first element and the second element of your given array, or like of the transformed array. You have fixed like first element will be 5, next last element will be 1. Now you are left with three elements which are 3 4 and 2, 3 4 and 2. And again, if you apply the same logic, you will say that this element, or like the second position of the z array, not second position of like this array, so this should be replaced with maximum of these remaining elements, which will be 4, and the second last element will be replaced by the minimum of this element, which is 2. Okay, so you have replaced 5 4 then 2 1, so the only position left will be occupied by 3. Now as you can see, this is forming a decreasingly sorted array. So by this, or by using this induction, you can prove that an optimal array will be one which will be decreasingly sorted. Okay, so it means that we have to convert this array into this array, and we need to try to find what can be the minimum number of adjacent swipes required. So you see that the first element is here we need first element to be 5, and here it is 5 only, so we don't need to swap anything. We move ahead, we find that okay, the next element should be 4, but here it is 1. So if you swap this 4 with 1, you will get, like if you swap these two adjacent positions, you will get 5 4 1 3 and 2. Then you move to next element, which is 3, so you need 3 here, but actually actually it is 1. So you again swap it, so you will get 5 4 3 1 and 2. Okay, now again you move to the next element, which is 2, but here it is 1, so you swap, so you get 5 4 3 2 and 1, and now you have got this array. So how many swaps did we do? So this is the first swap, this is the second swap, this is the third swap. So in total we did 3 swaps. So we can say that if the number of allowed swaps b is greater than or equal to 3, then the answer will be 1, otherwise it will be 0. So let us try to see how do we find the minimum number of adjacent swaps needed to convert the given array into a decreasingly sorted array. Okay, let us try to think on this. So let us try to think like, okay, let us see what happens if instead of sorting the array in a decreasing order, we were to sort the array in ascending order. So what will be the minimum number of swaps in that case? So you will find that the minimum number of swaps in that case would be equal to the inversion count. Okay, and inversion count is basically the number of pair of indices I and j such that I is lesser than j and ai is greater than aj. Okay, so it's kind of this thing. Okay, so let's say this is I, this is j. So as you can say, like this is forming an inversion pair, so we have to count the number of inversion pairs. So whatever is that number, we call it inversion count. So the number of swaps needed to sort the array in increasing order will be equal to the inversion count. But since here the array needs to be sorted in decreasing order, you cannot actually call it to finding the inversion count, but it will be similar to finding the inversion count, but this thing will be removed, and instead we will want the number of pair of indices I and j such that I is lesser than j and ai is also lesser than aj. Okay, so as we need decreasingly sorted array, you can say that the number of swaps, or you can say minimum number of swaps, will be the number of pair of indices I and j such that I is lesser than j and ai is lesser than aj. Okay, now how you can find this? Basically there are various options. Either you can do brute force. If you do brute force, then the number like the time complexity will be order of n square, or you can use Fenwick tree, or you can use segment tree, or you can say ordered set if you are using C++. So the time complexity, all of them would become order of n log n. Okay, but can we do better than this also? Okay, so if you try to see the constraints, you will find that all the elements of the initial array is only between 0 to 9. Okay, so you see such a small range of valid elements can exist, like all the elements can either be from 0 to 9. Okay, can only lie between this range. So we will try to utilize this property. So let us try to see how we can find the minimum number of swaps optimally. So for finding the minimum number of swaps, or you can say the modified inversion count, what we will do, we will iterate from 9 to 0. So you know the 9 is the maximum value of any element of the array which can be possible. So let us say that there are 9 at these places. Okay, now what we will try to do, we will try to find how many pairs of indices exist which will form the modified inversion count such that the right index will be here. Okay, so you see, if you have 9 here, then you are guaranteed to have all the elements which would be lying in this region will either be lesser than or equal to 9. Okay, since 9 is the maximum possible element, so all elements lying to the left of this 9 will either be lesser than it or equal to it. So what will be the number of inversion pairs or modified inversion pairs which have this element or this index as its right boundary? So if you say that LR, so if you say that LR forms a in modified inversion pair, then we are fixing this R and trying to find how many such possible values of L exist. So as you can see here, there are two such elements. So there is no 9 in this range. Okay, so all of them must be lesser than 9. So it means there are two inversion pairs. So here by inversion pair, I am again saying inversion pair does not mean AI is greater than AJ. Okay, so here I am saying that inversion pair is basically be pair which will form this kind of structure. Okay, that I is lesser than J and AI is also lesser than AJ. So this kind of pair we want to find. So here it will be 2. Now if you try to find the number of inversion pairs that will that will be having this as the right boundary, so that will be nothing but 1 2 3 4 5. So actually it should be 5, but it will not form inversion pair with this one. So this with these two will not form an inversion pair. So the number of inversion pairs ending at this would be 5 minus 1, that is 4. Okay, so here it is 4. Similarly for this 9, it would be equal to 1 2 3 4 5 6 7. So 7 minus how many elements are exactly equal to 9, that is 2. So 7 minus 2 is 5. So in this way you can find for every position of the 9 what is the number of inversion pairs which end at that point. Okay, which has that point or that index as its right boundary. So after doing it for 9, what we will do, we will just simply move to the next element, which is 8, then to 7, then to 6, like in decreasing order. From 9 to 0 you will just do the same thing for all the elements. But once you have done it for 9, we will also remove all these occurrences of 9 from our initial array. Okay, so let us say that if our initial array was looking like this: 1 then 9 then 2 then 3 then 9 then 3 then 2, like this. So after finding the number of inversion pairs with 9, you will remove these 9s. So next your array will look like 1 2 3 3 and 2. Again you will repeat the same thing for 8, then for 7, then for 6, up to 0. And after doing it for all the numbers, or like for all the possible values of elements from 9 to 0, you will simply keep on adding it, okay, at the same time. And whatever is the number of total number of inversion pairs you will get, you will simply check it or like compare it with B. If you find that B is greater than or equal to inversion count, okay, so in that case you will return 1, otherwise you will return 0. Let us now look at the code for it. So here we have defined a function int solve which will accept a vector of integers a and this b. So we define a vector of int current. So initially it will be equal to a. We also define a count, int is equal to initially 0. Then we iterate over the digits from 9 to 0. Okay, and then we have a variable called ind. So ind will initially be equal to 0. Then we also have another vector temporary. This is used for deleting all the, like, what will be the array after deleting all the elements which would be equal to this digit. Then we iterate over all the elements of our current vector. We check if current of I is equal to digit. If it is equal to digit, we add I minus ind to our count. So this count will basically store how many inversion pairs are there which has their right boundary element as this digit. Okay, so we just add I means how many elements are to the left of it, and from it we are just subtracting how many elements are there which are having value equal to digit. So I minus ind we will be adding this thing to our count. Then ind will be incremented by 1 since we got one element which is equal to digit. Otherwise, if the element is not equal to digit, then we just push this into our temporary vector. Now as you can see, we are not pushing any element which is equal to digit into temporary vector. You see, whenever the element is equal to digit, we are not pushing that element into temporary vector. We are pushing only those elements which are not equal to this digit. So after doing this thing, we will simply update our current vector with this temporary vector. Okay, and since we have stored the total number of inversions in this integer count, we will simply compare that if p is greater than or equal to count, then we return 1, otherwise we return 0. Okay, and this is the general format of taking inputs. Like we take input n, then define a vector of size n. Like we take all the elements of the array, and then we define a integer b, take it as an input, and then we simply print what is the value of solve of a comma b. Now coming to the complexity analysis, the time complexity of this approach will be order of n. The total space complexity will also be order of n, and the extra space complexity will also be order of n. Why it is total complex time complexity order of n? Because we are just iterating from 0 to 9, and then we are just iterating through the entire array. So in worst case it will be 9 into n, or you can say 10 into n. Since 10 is a constant factor, so we can just omit it. So you can say the time complexity will asymptotically remain order of n. Okay, similarly the total space complexity is order of n. We are using a space of order of n for storing the initial array elements, and again order of n elements for storing or like modifying the initial array. So extra space complexity is also order of n because of that modification. So you first of all modify the array and then again make the initial array this modified array. Okay, so that's why the extra space complexity will be order of n. So thank you for watching, and please like, share and subscribe our channel.